All right, guys. So a few chapters ago, actually, it was, I believe, in chapter 9, one of the things that we ended up doing was we defined the root mean squared value of a function. This was put into context of the root mean squared value of a voltage. And one of the things that I had briefly mentioned was that this was going to become important when it came to power calculations. We're now in a position where we can show where the RMS value or root mean squared value is going to be useful. So this section is going to be on the RMS value, root mean squared value, and power calculations. The first thing that I wanted to remind you of, and this is kind of a definition, is what is the root mean squared value? So root mean squared, or RMS value. And again, I'm going to do this with voltage, but keep in mind that it works perfectly well with current, with power, any other parameter of interest. So the RMS value, by definition, is the square root of 1 over the period, the integral from 0 to some time, of the function itself, quantity squared, integrated with respect to time, like this. And again, I take the square root of the entire thing, right? Now, this was particularly important when it came to sinusoids. And one of the things that we found was that for sinusoids, the root mean squared value was related to the amplitude through a very simple relationship that looked like this. So if you take the amplitude of the sinusoid, you divide it by the square root of 2, that's actually going to give you the RMS or root mean squared value. And this is where the voltage function takes on the general form like this. So let's be very precise about this, right? Now keep in mind that you can actually define the root mean squared value for different types of functions. It's not just sinusoids that necessarily have to go into here. You could have, for example, square waves, triangular waves, sawtooth waves, all sorts of other things, but this result only works for sinusoids. Now, to begin the discussion of power calculations, and the RMS value, I want to start with a very, very, very simple system. The system that I'm going to consider is going to be that of a resistor, and I'm actually going to place a voltage source across the terminals of the resistor in such a way that the voltage source is actually a sinusoid, the most general sinusoid like this. And the question that I want to answer is how much power is delivered to the resistor over one period. Right. And it's a relatively simple thing to actually calculate. So here the average power over one period, if you'll recall, is 1 over the period, the integral from 0 to t, the power as a function of time actually integrated, right? Now, we know that for this resistor as well as all other ideal basic circuit elements, the power itself can be calculated as the voltage times the current, right here. And we know by Ohm's law for the resistor that the voltage is equal to the resistance times the current, or the current is equal to the voltage divided by the resistance. So one of the things that I can actually do to simplify this is I can actually just place that straight up in there. Right. In which case, the average power then becomes 1 over the period, the integral from 0 to the period. And what we actually have is 1 over r v squared as a function of time integrated with respect to time. I'm going to do one last little thing. I'm going to bring this resistance out, and then I'm actually going to put everything into a parentheses. So here, I'm actually going to bring this out like this. Then I have 1 over the period, the integral from 0 to t. The voltage quantity squared. Whoops. Let's put the square on the outside like this, integrated with respect to time. Now let's take a look at what we have here. Go back to the definition of the RMS value. So the RMS value takes on the exact same form as what that is, except that the RMS value is underneath the square root. So what we actually have in this parentheses is 1 over r, 1 over the square root of 1 over t, v of t squared dt, whole quantity squared. This right here is the RMS value for the voltage, so what we actually have is the RMS value over R. So the average power delivered to this resistor when you actually have a sinusoidal voltage source is equal to the RMS value quantity squared of the voltage quantity squared divided by the resistance like this. Right? This is actually a very important result. Now, one thing that I also want to make mention of is that because this is a resistor, you can show through the exact same argument. Right? So by a very similar argument, it can also be shown that the average power is also the RMS value of the current squared times the resistance. Right? Notice that one of the things that I did was when I was calculating the power over here, when I split up the power into a product of the voltage times the current and I used Ohm's law to eliminate the current in favor of the voltage, I could have used Ohm's law to eliminate the voltage in favor of the current, and carrying out through the same calculations, you would have arrived at this same exact result that I'm highlighting here. I'll leave that as an exercise to you, but let's talk about what the significance of this is, right? What this is literally telling you, and this is one of the reasons why the RMS value is actually important, is that for a circuit with a sinusoidal source, so here we actually have a circuit with a voltage source that is a sinusoid. You hook it up to a resistor like this, right? And you compare it to a circuit with a DC voltage source. Like this, right? The power that is delivered to this resistor and that resistor with two different sources is absolutely the same, provided the RMS value of this source matches the DC value of that source, right? So this circuit over here with a sinusoidal source will deliver the same exact power as this DC circuit, provided the DC circuit and the RMS value of the sinusoidal source, provided those things happen to be the same. Right? And this is one of the reasons why we oftentimes use RMS values, because it allows us to make a very, very quick comparison to DC circuits. Now, on top of that, one of the important things is that when you take a look at the electricity that's coming out of your sockets, right, they'll always be rated with a certain voltage. So, for example, they might say it's 240 volts or 120 volts. There are certain appliances that are rated with a certain voltage as well. What they're actually giving you there is the RMS value of the voltage, right? So keep that in mind. Now, these RMS values, I also want to make mention of the fact that they go by a different name. So the RMS value of a parameter is also known as the effective value. This is just some nomenclature. So if you see, for example, the RMS voltage and the effective voltage, well, these two things mean the same thing. Similarly, suppose that you actually have the RMS current of something. This is the same thing as the effective current, right? So it's two different names that denote the same thing. Now, one important thing that's also that can be done is we can rewrite the real power and the reactive power in terms of RMS values as well. So suppose that you took a look at the real power that's being delivered to a system. Remember that the real power itself is the amplitude of the voltage times the amplitude of the current divided by 2 times the cosine of theta v minus theta I, in other words, the power factor. Notice that one of the things that I can end up doing is I can rewrite this thing as Vm divided by the square root of 2, Im divided by the square root of 2 times the cosine of theta v times theta I. But for a perfect sinusoid, Vm over 2, this is the effective or RMS voltage. And Im over the square root of 2 for a perfectly sinusoidal signal, this is I effective. So the average or real power can be calculated if you know the RMS value of the voltage, the RMS value of the current, multiply those two together times the cosine of theta v minus theta I, and you end up with another way of calculating the real power delivered to a circuit element. Similarly, by a similar calculation, the reactive power, right? Remember, it's Vm times Vi over 2 times the sine of theta v minus theta I. Well, this very clearly by the same set of arguments can be calculated as V effective times I effective times the sine of theta v minus theta I. So depending on what you're actually given in the problem, it might be more convenient to use the amplitude of something, or you can just go back to the RMS or effective value of something and then do similar power calculations. And we'll talk more about this in other videos.